Welcome back to this lecture on set operations. In this fifth segment, we will introduce a new proof technique called proof by containment or proof by mutual containment. And this proof technique is applicable when you're trying to prove that two sets are equal. So we say that any two sets S1 and S2 are equal if and only if F, the first one, is a subset of the second one and vice versa. I hope you agree with this statement. Now, if you want to prove that the sets S1 and S2 are equal, then you just need to prove this proposition and that one. Let's focus on one of them here, say this one. How are we going to prove the relationship of containment, which is to say that S1 is contained in S2, or S1 is a subset of S2? Well, we go back to the definition of subset, which says S1 is a subset of S2 if and only if, for all x, if x belongs to S1, then x belongs to S2. And to prove this, we just assume that x belongs to S1 and prove that then it must belong to S2. Now, this is how you prove containment of one set in another. So a proof by mutual containment is simply a double proof of first, this proof by containment, and second, this proof by containment. If you have proved both, you have proved that S1 and S2 are equal. And that is the definition of a proof by mutual containment. So let's illustrate this proof technique using the following theorem, which is one of the De Morgan's equalities for set theory. So let's write a proof by mutual containment. Notice the theorem is a universally quantified theorem that works for any two sets R and S. So first we'll pick two arbitrary sets, R and S, and then we're going to write two subproofs. One subproof to show that this set is contained or is a subset of that set. So how do we do that? We use the definition of subset or containment. Let's assume that X is any element in the left-hand side, meaning the intersection or the complement of R intersect S. And from there, we must prove now that X must belong to this right-hand side. And in this case, it's not really difficult. So what does it mean for X to be in the complement of R intersect S? Well, that means X does not belong to R intersect S. How could that happen? Well, the only way is if X does not belong to R or X does not belong to S, or both. If it's not in the intersection, that means it's not in at least one of them. But this in turn means that if X does not belong to R, then it must belong to its complement. And if X does not belong to S, then it belongs to its complement. So X must belong to the R complement, or X must belong to S complement. But if X belongs to one or the other, or maybe even both, then it must belong to their union. And that is what we were trying to prove in this case. So what we just proved is that if X belongs to the complement of R intersect S, then it must be the case that X belongs to the union of R complement and S complement. Now, up to this point, X is a specific but arbitrary element of the universe, so we just use universal generalization to infer that for all X, the conditional holds. And this concludes the first subproof of this proof by mutual containment. Let's write down the second proof on the right-hand side of the slide. So the second subproof is for the statement that this set must be contained or must be a subset of that set. So it's the other direction in the mutual containment relationship. So again, we're going to pick a random element of this set and call it X. And then we're going to have to prove that X must therefore belong to this set. So the proof is going to be essentially the reverse of the previous proof. What does it mean for X to belong to the union of the complement of R and the complement of S? Well, by the definition of union, it means that either X belongs to R complement or X belongs to S complement, or both. Which means that X does not belong to R or X does not belong to S, or both. I don't need to write down the or both every time. But if X does not belong to R or X does not belong to S, either way R does not belong to their intersection. And that's the next inference. And if X does not belong to R intersect S, then X must belong to the complement of R intersect S, by definition of complementation. And that is what we were trying to prove in the second subproof, namely that X belongs to the set on the left-hand side. So we just proved the conditional that if X belongs to this set, then it must also belong to this set. But X is just one arbitrary element of the universe, so let's generalize over the whole universe. And we now prove the containment of this set inside that one. And since earlier we proved the containment of this set inside that one, we just concluded the proof by mutual containment that these two sets are indeed equal. So make sure you get comfortable with the proof by mutual containment, which will be applicable and useful to you in other computer science classes, for example in CS 381 if you happen to take it later. And this concludes this segment on proof by mutual containment.